Hello everyone. Good morning, good afternoon, good evening, wherever you're joining from around the world. Hope you're having a great TPS 2022. Welcome to the session on Azure SQL availability and resiliency for modern applications. My name is Rajesh and I'm a senior product manager working at Microsoft. I'm joined by two of my colleagues who also work at Microsoft. Scott Kim, he's a principal product manager, and Sudhir Raparla, who's a senior product manager. In this session, we'll have a quick overview of what high availability and disaster recovery is all about. Then we'll touch upon local resiliency, uh, and then go over zone resiliency, and then we'll look at disaster recovery, which falls under the bucket of geo resiliency, and then we'll wrap it up with restorability and have a summary towards the end. Along the way, we also have a bunch of demos to keep you engaged. Uh, if you think about what is high availability and business continuity for any modern application, any application needs to be resilient to software upgrades that happen all the time in the public cloud. So when these upgrades go over under the hood, your applications needs to make sure that they are resilient to these kind of upgrades. In fact, many of the cloud providers do also give you an option to have fixed maintenance windows wherein you decide the time when the maintenance happens, and then none of the maintenance happens outside the windows that you specify. There are also all kinds of equipment failures that happen in the public cloud. So when these kind of issues happen, we'll need to make sure that your databases are resilient to hardware failures, and then they quickly move over from a bad node to a healthy node. There are things which happen outside our control, like natural disasters. In those situations, you might look for a scenario where you are looking for resiliency, which is at a zone level, where you want a different zone which is physically separate from the first zone to take over if the first zone is lost. And towards the end, there's also possibility that there are many user errors that happen along the way. So you need to make sure that if things go wrong or if there is any user error, you have a way to go recover and restore from your data. Azure SQL has industry-leading high availability and reliability guarantees, and all this is done by abstracting the complexity to the end user. All that you have to do is do a bunch of clicks, and then you enable high availability and disaster recovery. And SQL has a layered resiliency model, wherein every database within the region has a built-in high availability. If the region has zones, then you land up in one zone. If the region doesn't have zones, you still get the built-in high availability. And then you can expand it from the local resiliency, then you start expanding it into zone resiliency, where in regions where we support availability zones, you can have SQL database provisioned in multiple availability zones. So in the event of one zone going down, you still have the database being brought online on a different availability zone. And we also provide industry-leading SLAs in order to back up the availability numbers that we publicly list. Let's look at the layers of resiliency. As I explained in my previous slide, you start with one data center and then one zone in a data center. As you can see, in a single availability zone, we still guarantee built-in HA for every SQL database that is provisioned. So if the SQL database or if the node on which the SQL database goes down, if there are any hardware failures, if there are any unforeseen planned or unplanned maintenance events that happen, what will happen is we'll make sure that the DB becomes online on a different healthy node, and then there is least disruption to the application. Let's say if you want to expand this local resiliency to a zone resiliency. In this case, you are looking at 3 availability zones in regions. There are in Azure we currently have about 25 odd regions where we support availability zones, and in availability zones, what will happen is you will have 3 separate zones which are physically separate. Each one will have its independent network, power, and cooling. So that way you will have multiple. There is no single point of failure across all of these 3 availability zones. In this case, the SQL database, the data layer, or all the components of the SQL database are spread across multiple zones, so you don't have a single point of failure. And if you are looking at, let's say, what happens if the entire region goes down, then you can protect it by having a GeoDR copy for your primary region, where you have your primary region, and then you set up your secondary on a geo-paired regions. Right? With that, let me hand it over to Scott to talk about local resiliency.
Hi, my name is Scott Kim from Microsoft, and I'll be walking you through the SQL maintenance window feature set today. To share a bit of background about the maintenance process, SQL periodically performs planned maintenance of SQL database and SQL managed instance resources. Now, these maintenance events do not happen frequently, but typically once every 35 days or so. Underneath, SQL batches all required maintenance into a single maintenance event to reduce customer impact. These include SQL Server updates, Azure Service Fabric updates, as well as guest and host OS updates of the underlying VMs. During these maintenance events, databases are fully available for use, but they will experience short failovers as the updates are applied. Typical failovers are completed within seconds, but we understand this can be disruptive in some cases. With SQL maintenance window features, users now have options to select from preset maintenance schedules, which helps make impactful maintenance events predictable and less disruptive. By default, SQL applies maintenance updates only during 5 p.m. to 8 a.m. local times per region to avoid peak business hours. Users can now select the weekday option or a weekend option depending on their business need. If the weekday window is selected, SQL will ensure all planned maintenance activities will only occur between 10 p.m. to 6 a.m. local times Monday through Thursday. For weekend option, updates will only take place during 10 p.m. to 6 a.m. local times Friday to Sunday. So a common question we get on this is, does selecting a weekday maintenance window mean SQL databases get updated every weekday? The answer is no. It means when there is a need for maintenance, Azure SQL will make sure it happens only during the selected weekday maintenance window hours. Additionally, there can be instances where a maintenance event does not finish within one window. For example, assume for a database with weekday maintenance window enabled, SQL starts on Tuesday at 10 p.m. but does not finish by 6 a.m. Wednesday. Then these maintenance activities will be paused at a safe point and continued on Wednesday at 10 p.m. Along with SQL maintenance window, users can set up alerts for upcoming planned maintenance 24 hours in advance using advanced notification feature. For example, let's assume a user has a weekday maintenance window set up for their database along with alerts. If there's an upcoming planned maintenance for Wednesday evening, alerts will be sent 24 hours in advance on Tuesday, along with alerts on starts and completion of the maintenance events. Alerts can be configured as text, emails, push notification, and voicemail, and the history of these alerts can be viewed in the Azure Service Help blade. SQL maintenance window feature is free of charge and works for most of the SQL offerings, but there are some exceptions that are noted in our documentations. This is a high-level view of how Azure SQL maintenance events are carried out. The key call-out here is that SQL updates one replica at a time, and these updates are performed in stages. At each stage, upgrade is only applied to a subset of a cluster called upgrade domains, with each UD carrying no more than one replica, which ensures that applications remain available during an update. For business-critical and premium databases, at least one secondary replica will be online to ensure no client downtime. When the primary replica needs to be brought offline for maintenance, a reconfiguration process will ensure that secondary replica will become the new primary replica. For general purpose and standard databases, the primary replica will move to another updated compute node with sufficient capacity. SQL maintenance window works by grouping Service Fabric clusters by maintenance window schedule and placing the SQL databases according to this selection. When a user database selects a weekday window in West Europe, for example, the databases will be placed in the cluster with that exact maintenance window schedule. So now let's talk about how to set up SQL maintenance windows. Setting up maintenance windows is straightforward. During database create, maintenance window selection could be found under additional setting, where selection can be made from the maintenance window dropdown. Setting up maintenance window for existing databases can be done under the maintenance blade. And PowerShell as well as CLI supported as well. An important note here is configuring maintenance window is an operation very similar to changing the service tier of the Azure SQL database. The resource is fully available during the operation. However, a short failover will occur when the reconfiguration happens at the end of the operation. So it is advised to perform the setup during off-peak hours.
Thank you, Scott, for the overview on maintenance windows. Now let's look at architecture for various service tiers of SQLDB, and we'll specifically look at high availability architecture. As a quick refresher, there are primarily three main service tiers. Obviously in the DTU you will have the other model, but in the vCore model you have service tiers like general purpose, business critical, and hyperscale. Here's the high availability architecture for general purpose. This behaves more like a failover cluster instance. It's analogous to what you will see to an FCI in on-prem. In this case, what happens is you have the primary replica. The data files are connected on a remote storage. So you will have the data files residing on Azure Premium Storage. It could be on local redundant storage where you have your data and log files. Your backup files are always geo-redundant by default. So they sit on a storage account type, which is RAGZRS. And then you'll have spare nodes with capacity. So in the event of failover, SQL Server data files are detached from the primary replica, and then one of the nodes with the spare capacity gets into action. The data files get attached to that node. The compute is spun up, files get attached, and then users get reconnected to the same database. And then there is also connectivity redirection, which is built in. Let's look at architecture for business critical. So this is based on always-on availability groups. Pretty much exactly what you know in the on-premises always-on availability groups. We implemented something similar for the business critical service tier. In this case, you'll have one primary and then three secondary replicas, which are automatically created. And then, as you can see here, you will get an always-on availability group on all the four replicas. On each of the primary replica and the secondary replicas, you will have the data and the log, which is locally sitting in the same node as the database. Backup files are geo-redundant by default. At least we'll make sure that when any writes are happening, at least one secondary is in sync with the primary. And the automatic failover that happens between the primary and secondary, all of it is handled based on SQL and Service Fabric. Recovery is extremely fast because this is always on availability group. You always have a secondary replica which is completely in sync. So it's just a matter of seconds when the switch happens from one node to the other node. Since it's also an always-on availability group with a bunch of secondary replicas, we enable one of the secondary replica to be used as for read scale. So you could connect with an application intent equals read only, and then directly get routed to one of the secondary replicas for offloading your reads. All right. So with that, let's get into the architecture for hyperscale. This kind of gets very busy, so I'll go over one step at a time. So at the top of the hyperscale architecture, you have the compute. So you have your primary compute, and then you can have up to 4 secondary computes. And then down below, you have your page servers. So these are again paired page servers. So for each of the paired one, we do have redundant page server, which is right behind it. And then down at the bottom, you will have your data files, which are sitting in the Azure storage. And then we also take database backup snapshots on the Azure storage. So that way, this is all limited on the Azure storage accounts. By default, it will be RAGRS, but you can also change the storage type. And then you also have the log service. What will happen is the log service is the one where all the log transactions commit. They land on that. We convert them to long-term storage for destaging, and then log service is the one that serves log records for all your secondary servers and for all the paid servers to catch up. All right. With that, let's look at high availability architecture for zone resiliency. In case of zone resiliency, as we talked about in the earlier slides, in a particular region, you will have three physically separate zones. These are physically separate, so you will have each one of them have its own network, power, and cooling. So you will avoid the cases of a single point of failure. Right? And then we also have the Azure Management Services, which are replicated across all three zones. Now let's look at the same architecture that we looked for the various service tiers in terms of how they fare when you're looking at a zone resiliency. So we recently announced general availability of general purpose SQL DB zone resiliency in 4 regions, which is West Europe, North Europe, West US2, and France Central. And we have a bunch of regions where we are still in preview. We are aggressively looking to GA in these regions as well. As we learned earlier, the storage for general purpose service tier is remote storage. So in this case, what will happen is the storage is zone redundant, meaning irrespective of whether the compute sits on zone 1 or zone 2 or zone 3, data is always replicated across all the 3 zones. Right? So this will help. This will ensure that in the event of failure, you have zone resiliency for the SQL database. And then your backups, which are again by default sent to read access GRS accounts. Right? And the event of failover, you can move from zone 1 to zone 2 or from zone 1 to zone 3. So when a failover happens, the compute gets pinned up on a new zone, the data files get attached, and then the DB goes through the recovery, and then the DB comes back online. All right. So let's look at zone redundancy architecture for business critical service tier. As we learned in business critical service tier, we have always on availability groups. In this case, what we do is we place the replicas in 3 availability zones. So 2 replicas will be in one zone, the third one will be in zone 2, and then the fourth one will be in zone 3. So that way, there's no single point of failure, and data gets replicated across all 3 zones. So this is zone resiliency for business critical tier is completely free. There's no additional cost for it, and it also gives you a higher SLA than the regular SQL database. We by default guarantee 99.99%, but for zone redundancy business critical service tier, we up the SLA to 99.995, which is again industry leading, if you will. All right. With that, so if there is a failover that's happening, then we'll move the primary replica from one of the zones to a secondary replica, which is in different zone, and then the failover is also very fast because we always make sure that data is always synchronized between these replicas. All right. So let's look at the hyperscale architecture in a zone redundancy. So this is currently in preview. We are aggressively looking to make it generally available. Because of all the components in hyperscale, we need to ensure that with all the components that exist in hyperscale, all those components are zone redundant. As you will see in this diagram, so on the primary compute, on the compute layer, what we do is we make the primary and the HA replica, place them in separate zones. So when you enable zone redundancy for hyperscale, you have the requirement to have at least one HA replica. So this is one of the requirements in order for you to have zone redundancy guarantee for hyperscale database. Right? And then on the paid servers, as you can see here, for each of the paid servers, like in this case, the colored ones, the blue ones, the paid server 1, replica 1, each one gets placed into independent availability zones. So that way there is no single point of failure. And then on the storage layer, we use zone redundant storage or geo zone redundant storage. So these will ensure that if there is a failure on one zone, then the other zones still have the data to serve from. And then as with the last component, with the log replica, we also do we make sure that these log replicas are placed in 2 separate zones. So that way there is no single point of failure even for the log as well. Today this is all supported for a new database which you want to create with a zone redundant hyperscale database. It can only be specified during creation, but you can use any of the methods like a database copy, point in time restore, or a geo-replica if you want to update an existing hyperscale database that's not zone redundant, but you want to convert it into a zone redundant hyperscale database. Uh, in, in future, we'll soon enable a feature where you can update a database in place from a non-zone redundant to a zone redundant hyperscale database. All right. So with that, let's look at a demo for a failing over a hyperscale database. So let me get into Azure portal, and then I'll show you the database that we are going to initiate failover on. So let me go to the database. The database is called DPS demo DB. Once it loads up, we'll quickly check if it's zone redundant or not. So let's go to the JSON view here. You might see the property which says zone redundant. That's true. And then, as I mentioned in the slide, you need to have at least one HA replica for a hyperscale database to be zone redundant. So we have one of them checked out, right? So now let's go and initiate a failover for this database. What we really want to see is how does the database behave when we initiate a failover, and this is a manual user-initiated failure. So this is for you to make sure that if you want to gain confidence on what is happening to the database, or if you want to test some resiliency of your applications, and if you want to have controlled database failure. So this is as part of your test. In a real world scenario, if something of this nature happens behind the scenes, you will have the database move from zone 1 to any other zones in that region. All right. Okay. So before we do that, let me go ahead and start a simple query which just gets a date. It connects to the same database, and then it spits out the date time once in every 3 seconds. So the idea here is as we initiate failover on the hyperscale database, you will see an error when the database gets stopped on when the primary compute when the primary compute is killed on one particular zone, and then the failover happens to one of the HA replica. All right. So let's go ahead and initiate the failover, and here I'm using a PowerShell command, and this PowerShell command is invoke AZ SQL database failover. All that I'm doing is I'm passing in the resource group name, which is my resource group name. I'm giving it the server name, which is the server name on which the database exists, and then the name of the database. Once the PowerShell command kicks in, which as you can see here, it just happened, then you will see on the SSMS window an error which is clearly saying, hey, here's an indication that the database has just been initiated for a failover. Right. All right. So with that, let's go back into the activity log, and then I'll also show you a couple of things before we try connecting to the database again. So let me go ahead and refresh this, and then this was one of the failure that I initiated a few hours ago as part of prepping for the demo. You will see an entry where it says issue failover on the database, starter accepted, and then the command will be asynchronously completed behind the scenes. Right. So let's go ahead and try connect to this database. So let's say, let's start from T1. Let's run this query. We'll make sure that we are able to connect to this database after the failover. As you can see here, this was how simple, how seamless it was when you manually initiate failover, but then it drives across the message, and then it also gives you the confidence that, hey, for a database that is zone redundant, you can go ahead and failover the database, and then have confidence that, hey, when the database fails over, it is moving from one zone to another zone in the same region. Right. So with that, let me go ahead and get back into the slide. Alright, so that was the demo on hyperscale high availability failover for a zone redundant database. Let's talk about the other topic, which is zero resiliency. So what zero resiliency talks about is, let's say if you have a scenario where your entire region is going down, you typically want your database to be up and running on a region which is different from your primary region. So you need to have some kind of data replication, which is active geo replication in case of SQL DB, that's going between your primary and your secondary regions. Uh, so what does cross-region replication provide you? So it's an ability where you can create GeoDR links between your primary and secondary region, and you can use it on single databases or pools, and then you can also use it on top of auto failover groups. So active geo-replication is the underlying layer, and then you can abstract it by creating auto failover groups. Auto failover groups, think of it as nothing but always on availability groups, where you get a mechanism to group a bunch of dependent databases if those databases are needed for your entire application to work together. So you can put a bunch of databases in a failover group and then treat them as one bag of databases, which will move from primary to secondary in case of a disaster recovery. Right? All the secondary databases, they provide database level recovery solution. In ideal world, you can use the secondary databases for load balancing. So if you want to offload your reads, you can send those read workload to the secondary databases, or you can also replicate the secondary databases to anywhere in the world, depending on where your users are. This has been made generally available for hyperscale recently. It was generally available for the general purpose business critical and other service tiers for a very long time, but we were very happy to announce the general availability for hyperscale in June of 2022. Right. Quick comparison between active geo-replication and failover groups. I know we have seen many customers asking us, hey, what are the big differences between geo-replication and auto failover groups? Both of them serves the same purpose. It's just that the way of abstraction and the grouping that goes on between one versus the other. And just a reminder, auto failover groups uses geo-replication under the hood. So geo-replication is the underlying fundamental block which helps you to replicate data between a primary and a secondary region. So in order for you to have automatic failover, you need to go with auto failover groups. If you want to failover multiple databases together, which I explained in the previous slide, auto failover groups was primarily designed for handling scenarios where you can put a bunch of databases in a group and then treat them as one logical unit. Auto failover groups also gives you a mechanism where you can have a single listener for read write and read only. So you don't have to update your connection strings, which is one of the neat benefit for failover groups. We also have it supported for managed instance. So this is only supported for managed instance auto failover groups. You will not have geo-replication supported for managed instance. And then if you want it to be in a same region as primary, you can go the route of geo-replication. But for auto failover groups, since we rely on DNS, it has to be on a different region than the primary. And then you can also have multiple replicas for geo-replication, but for auto failover groups, you can only have one secondary for each. If you have a primary, you can only have one secondary, and then both of them support read scale. Let's look at the architecture for geo-replication and failover groups. What you will see here is you have your primary SQL database, you have your application read-write traffic coming to it, and then you will have a geo-replication link where data gets replicated from your primary to your secondary region, and then you can route your read-only traffic to the secondary region. In the event of the failover, the role switch will happen, and then the secondary becomes primary, and then the connection string will have to be changed if you want to route your applications to the new primary. On the right hand side, all you have is auto failover groups, and this is exactly similar, other than the fact that here what we are trying to do is we are putting a bunch of databases and grouping them into one unit. And in this case, the difference between the geo-replication auto failover groups is its advantage to have a dedicated listener. As you can see here, you will have a dedicated read-write listener and a read-only listener. So in the event of failover, your connection strings will still remain the same, and you will use the same listener endpoints that you used before the failover to connect to the database that is primary, and you don't have to worry about which one is primary, because this is all transparent to the application. All right. With that, let me hand it over to my colleague Sudhir, who is going to talk about restorability.
Hi, I'm Sudhir Raparla. I'm from Microsoft Azure SQL DB team. In this session, we're going to do a deep dive on backup and restore capabilities on Azure SQL DB. Database backups are an integral part of your business continuity and disaster recovery strategy, because these backups allow you to recover from scenarios like regional outage, accidental deletion, ransomware attack, and much more. At a high level, Azure SQL DB provides two types of backups: point-in-time backups, also known as short-term retention backups, and long-term retention backups. Point-in-time backups are retained up to 35 days of retention period, whereas long-term retention backups can be retained up to 10 years. Let us see different types of restore features or capabilities enabled by short-term and long-term retention backups. Point-in-time restore. Point-in-time restore is enabled by point-in-time backups. Imagine a scenario where there is a ransomware attack or an accidental deletion, and you would like to restore your database to a baseline or a certain point in time. Point-in-time restore functionality allows you to do just that. It allows you to restore your database to any given point in time within the configured duration, down to a second level granularity. Long-term retention backups, on the other hand, provides you restore capabilities beyond point-in-time restore timelines. These backups or these restore capabilities are very helpful in scenarios where you have to meet your compliance, auditing, regulatory, and other business requirements. Geo restore capability. Geo restore capabilities help you recover from a regional outage scenarios. It restores your database to any logical server, either within the paired region or any other Azure region. Now let us see how each of these restore functionalities work in detail. Point-in-time restore. Point-in-time restore functionality is enabled by point-in-time backups, also known as short-term retention backups or automatic backups. In Azure SQL DB general purpose and business critical service tiers, full backups are taken every week, differential backups are taken every 12 or 24 hours, and log backups are taken every 5 to 10 minutes. On Azure SQL DB hyperscale service tier, we use snapshot-based backup methodology, where changed blocks are captured as part of snapshot backups and automatically stored in the storage. Irrespective of the service tier, these backups are taken automatically and stored in read access geo-redundant storage by default. Users can restore their databases by themselves using these automatic backups. They can use Azure Portal, PowerShell, or CLI to restore these backups. Like I mentioned earlier, these automatic backups or point-in-time backups helps user restore a database to a certain point in time down to a second granularity. And these restore operations create a new database and they do not replace the existing database. Users have complete control over the retention period of these backups. By default, point-in-time restore is enabled with 7 days of retention. However, users can configure it from 1 to 35 days based on their business requirement. Now let us see how these point-in-time backups help you restore deleted databases. Imagine a scenario where you accidentally deleted a database and you would like to restore that database immediately. Point-in-time backups allow you to restore a database either to a point just before the deletion or to any point within the configured point-in-time retention. This restore workflow creates a new database in the same logical server. You can choose to name the restored database same as original database. This is very helpful in scenarios where you have hard-coded your database connection strings or database name in your application layer. After you restore this database with the same name, you do not have to make any change in your application layer and continue to use it the way you did before deleting the database. Now let us take a look at long-term backup restore. Long-term backup restore is enabled by long-term retention backups. Long-term retention backups are full database backups. They can be retained up to 10 years. That means you can restore your database using these long-term retention backups for up to 10 years. These backups are stored in read-access geo-redundant storage by default. Users can use the long-term backups to restore the database using Azure Portal, PowerShell, CLI, or API. And the restore operation creates a new database either in the same logical server or a different logical server based on user's choice. And users have complete control over the backup frequency and the retention duration. For example, as part of this long-term retention, users can choose to take weekly, monthly, and yearly backups. They can also mention the duration for which of these weekly, monthly, and yearly backups need to be retained. Long-term backups are not enabled by default. Users would have to configure the backup frequency and the retention duration to enable long-term backup capability in Azure SQL DB. Now imagine a scenario where your database and the backups are sitting in a single region and there is a regional outage. It can lead to total data loss. To protect you from such scenarios, Azure SQL DB provides a functionality called backup storage redundancy, which lets you replicate your backups to either different data centers or availability zones or a different geo region. Different redundancy options available are locally redundant, which replicates your backups 3 times within the same data center. Zone redundant replicates your backups to 3 different availability zones within the same region, and geo-redundant backup storage redundancy replicates your backup to a paired region. Depending on your data residency requirements and the high availability requirements, you can choose any one of these backup storage redundancy options. As I mentioned earlier, Hyperscale uses snapshot-based backup technology. As a result, both the database and the backups share the same storage account. So backup storage redundancy option on Hyperscale is applicable for both the database as well as backups. Please note, prices for these different storage redundancy options are different across different regions. For more details, please visit the pricing page. GeoRestore. GeoRestore allows you to recover your database from a regional outage scenarios. It supports an RPO of up to 1 hour. And GeoRestore capability is available only on databases with backup storage redundancy set to geo-redundant backup storage. How does this work? When you set geo-redundant backup storage as your backup storage redundancy, the database backups are automatically replicated to a paired region. Now user can use the database backup in the paired region to restore the database within the paired region or to any other Azure regions. And users can perform GeoRestore operation using Azure Portal, PowerShell, or CLI. This restore operation creates a new database in any region in the same subscription. Let me take a pause here and summarize what we have discussed so far. Azure SQL DB provides 2 types of backups: point-in-time backups and long-term retention backups. These backups enable different types of restore features like point-in-time restore, deleted database restore, long-term backup restore, and geo restore. Now let us go through a quick demo to understand how point-in-time restore works and see it in action. Here I have a database called testdb1, and late last night I made a change on this database due to which there were a lot of errors in the application layer. And I would like to restore the database to a point in time before I made those changes. To do that, I'll go to the database page and click on Restore. In the restore workflow, I can select the restore point. This database has a point-in-time retention set to 7 days. As you can see, I can restore this database to any point within the last 7 days. Since in this case I know that I made a change at around 11 p.m., I would like to restore this database to say 10 p.m. to be on safe side and at the same time to minimize my data loss. So to do that, I will select 7:29 and choose 10 p.m. as the restore time. Review all the settings and click on Review plus Create. Once all the settings are reviewed, you can click on Create button to restore the database. Please note, this restore operation does not replace the existing database. It will create a new database in the same logical server as the original database. Based on the restore point you selected, a full database backup, relevant differential backups, and the log backups that would help you restore your database to that point are selected, and a restore operation would be performed using those backups. While that is running, now let us imagine if you want to restore a database to a point beyond the configured retention. How would you do that? To do that, you would have to increase your point-in-time retention period to a desired value. To change point-in-time retention, go to Backups page under the Data Management section in your logical server. The Available Backups tab lists down all the available databases, earliest point-in-time restore point, LTR backup information. If you'd like to change the point-in-time retention for any of these databases, go to Retention Policies tab, select the database for which you would like to change the retention. In this case, I want to change the retention for hyperscale database and click on Configure Policies. By default, point-in-time restore is set to 7 days for any database. However, users can change it to any value between 1 to 35 days. In this scenario, let me update the point-in-time retention for this database to 25 days. Click on Apply. This will update the point-in-time retention setting for this database to 25 days. As you can see, the point-in-time retention is now updated to 25 days. If you set long-term retention backups, or if you configure long-term retention backups on this database, you would see the weekly, monthly, and yearly backups and their corresponding retention schedule. Now let us go back and check if the restore operation is successful. Yes, the restore operation is successful, and we successfully restored a database to last night 10 p.m. Now let us see how this point-in-time restore functionality helps you restore deleted databases. To view the list of deleted databases, go to Deleted Databases page under the Data Management section in your logical server. Here in this case, I deleted this database accidentally early this morning, and I would like to restore this database to a point in time just before deletion. To do that, I'll click on this database and it takes me to restore database workflow. Here I can select the source as point in time or long-term backup retention. Point in time source would help me restore a deleted database from point in time backups, whereas long-term backup retention would help me restore a deleted database from long-term backups. In this case, I want to restore the database from point in time. By default, the restore point is set to point in time just before deletion. However, you can choose any point in time in the configured retention period. In this case, I am leaving it as it is, as I want to restore this database to a point just before deletion. The database name, I can either leave the database name as is or change the name to original database. This is very helpful in scenarios where you have hard-coded your connection strings and database name in application layer. With the ability to rename this database to original database, you need not make any change in your application layer and can ensure that it works seamlessly. Deleted database restore operation creates a new database within the same logical server with the chosen name. Let's click on Review plus Create. Sometimes, as part of compliance requirements, you would need to view the list of all available database backups to ensure that you have enough restore points to help you restore to any point within the desired retention period. To enable you with that, we have introduced a new feature in Azure SQL DB called Backup History. Backup History lets you view all the automatic backups or the point-in-time restore backups that are taken on your database. To view the list of all point-in-time backups on your database, you can connect to your database using SSMS and query a DMV called sys.dm_database_backups. This DMV lists all the point-in-time backups available on your database. This DMV contains information like backup file ID, database GUID, physical database name, physical server name, backup start date, backup finish date, backup type, and whether the backup is in retention or not. The backup underscore type indicates whether this is a log backup, a full backup, or a differential backup. D stands for database backup, full backup. I stands for incremental backup, and L log backup. As you scroll down, you will find some database backups that are out of retention but still displayed in this DMV. The reason being, sometimes when we have to perform a restore operation, you would need backups that are older than 7 days to perform the restore correctly. For example, if I have to perform a restore to this point, I would need the full database backup, this incremental backup, and all these log backups to restore to that point. So to summarize, in this demo, we have seen how point-in-time restore works, how to configure point-in-time retention, how to restore a deleted database using point-in-time restore, and how to view all the point-in-time backups for a given database to help you meet your compliance requirements. Thank you. Hope you have enjoyed this session.